Hello everyone. Thank you so much for having me here. I'm Yamin. I'm currently a third year, third year PhD student in Vanderbilt University Nerdy Lab. And today I'll be talking about getting started with the latest machine learning approaches and guiding you through the journey that bridges research papers and actually running the state-of-the-art code. And what we learn in this workshop. So first, you will know where to find this cutting edge deep learning or machine learning research papers, and how to find this, utilize the right resources, how to get started with the repo and run inference and train these models. And as a part of this session, we are going to run a state-of-the-art code demo together, which is published in last year's NeurIPS. We are going to use this model to translate the raw EEG signals into the corresponding fMRI time series into thalamus, just showcasing a real-world example of applying state-of-the-art deep learning approaches in neuroscience. Okay, let's start by step one, finding the right paper. This is a very critical step to stay updated with the latest research. So besides the platforms like Google Scholar, Archive, or preprints, one thing I would like to especially mention is that if you want to know or learn the latest or the greatest things in deep learning research, you definitely want to check out this top conference proceedings in deep learning area like NeurIPS, CVPR, ICML, ICLR, and MICAI. And this conference often establish the benchmark for all the novel method and have plenty of brilliant ideas there. So these are all the invaluable resources for people who want to keep up with the latest trends in deep learning. And moreover, these kind of conference encourage the culture of open science. So they want to promote the transparency, collaboration, and reproducibility in the community. So they often encourage the author to submit their code and data set as well along with their submission. So luckily or hopefully we can find the link to these resources in their paper. And talking about open science, Open Review is another platform that you could see ongoing reviews there. So for example, for conference like iClear, you can see all the discussions even during the review period. And for the conference like NeurIPS, I think they also publish their discussion and review as well, but it's right after the paper decision session. Yeah, and these are all the very useful resources for you just get to know what's the pros and cons of that paper if you are reading that paper by yourself. Yeah, and the second strategy here is to follow the citation trails, which means you could find the related works by checking the reference and citations. For example, here is a very latest paper about EEG foundation model, which is called Labram, and it is published in last year's iClear. And 1 year passed, I would like to see if there's any new EEG foundation model came out. So I just click the cited by button here to see which paper cite this paper. So here it is. So we could find there is a foundation model words in the title of this paper. So this is based hopefully the one I would like to check it out. And another example here is a very famous vision transformer paper. So it's quite popular. It has been cited for like 53,000 times, and it's a very long paper list. And what if I want to see which paper in my field use this kind of like deep learning architecture? So we could click this button again and search within the citing articles. And then I type fMRI here, and it just gives me all the papers that related with MRI, fMRI, and probably use vision transformer in their paper. And last but not least, you could leverage the social platform, which means you could follow researchers' social media on Twitter, LinkedIn, and GitHub just to stay tuned with their latest update about code or their following work. Okay, after we find a paper, we are interested in the associated resources their like code and data set and a model checkpoint, etc. So usually you could find this information in the footnote, abstract, and reproducibility statement and experiment in this paper. So first of all, GitHub, it is where usually people put their code, and you could easily find it like type the GitHub and code to just keyword to search in the paper. And many papers would have a very good project page with official link to all the resources you needed, like code and data set. And this link usually appear like right after the author list or in footnote or abstract. And of course, the data set and model checkpoint, this information will usually appear in their GitHub repo. And now I think more and more people tend to upload their data set and pretrain with on a platform called Hugging Face. So in the demo we are going to play with later, we are also going to download all of the resources from Hugging Face. So it's a good practice. Okay, so since this workshop is mainly dealing with the GitHub repo, so these are types of GitHub repo you might find. So type 1, coming soon repos. Yeah, this repo can be really frustrating when you first see this, but there's one thing you could check is the last commit date. So if it's very close to the current date, maybe that's fine. You could just stay updated or just ask author for code. But as you can see here, it's like 2 years ago. So I think the author of this repo is not going to update the anymore. And type 2 messy repos, I didn't find an example here, so I just asked GPT to generate this kind of picture so you get an idea of how this repo might look like. And we definitely don't want to build our own work on this type of repo either. Yeah, and here are 2 examples of very clear and clean examples. So one is came from a model called BIOT, which is accepted by NERVS 2023. And this is a very new time series foundation model. So as you can see here, their file and folder are very structured. And very good thing of this repo is that they have very good example file and tutorial just to help you to quickly get started with your repo. And also they have a very clear README file. So here I only just screenshot parts of their README. So basically you can get the idea that they have a very clear instruction about how you can get started with their code and how to install the model or environment and how to initialize the model and where you can find all of these tutorials. So you could actually go to the repo itself and do here as the BIOS model I mentioned. So overview, quick start, folder structure, pretrain models, performance, something like that. And for the moment libraries, very similar. And yeah, they just have all these details ready for you to use. Okay. And yeah, and assume you have find the GitHub repo you want to run. There's a few things you need to check before running. So first, you need to check about the environment. So just make sure you have installed all the dependencies and requirements just as like the repo said. And we usually recommend you to install all of this library under virtual environment, so then you won't mess up with the other project you're working on. And the most important thing here, I think, is to ensure you are using the correct Python version in your virtual environment just to match with the original repo. Yeah, and second thing here to check is the data format. So usually many repo would have sample data, but if you are using your own data, just make sure to verify the input data formats match the repo's requirements. And of course, you need to preprocess your data as per instructions in the documentation. Third, the hardware requirements. So some repos might require GPUs with very high memory or multiple GPUs just to make sure your machine can support this kind of training before you start. And one thing I would mention here is the hardware mentioned in the paper may not necessarily indicate the minimum requirements for training the model unless it's super obvious, like you don't want to train a large language model on a single GPU, right? And or it explicitly stated as required. So you can always like check it out by running the model on your machine and see if it will give you any like error message. Yeah, and inference also usually requires significantly lower GPU resources compared to training. Sometimes you can down it, made it down on CPU. And if you luckily have multiple GPUs, you probably want to check if the distributed training is supported. Yeah, and for code compatibility, you need to check if this repo can be run on your operation system. So for example, here is a very popular deep learning model called Mamba, which is released by the end of 2023. And I think they have requirements here. Their code can only be run in Linux. Yeah, and the last, but I think is the most important thing here is GitHub repo issue is your friend. So before you actually run the code, just take some time to check and browse the issue list, which usually appear in here in the GitHub repo, just to see if there is any like ongoing changes of the code. Is there any unsolved problems there, any bugs? And let's see the example here. So for this repos issue, they only have 8 opening and have over like 100, like 500 close issues. So this is actually a very good sign because it tells you that like the authors of this report are very actively managing the code base. So it's kind of reliable, and you might probably want to build your own work upon this kind of like report. And another thing is here, which the number of folk and stars, it kind of tell you like how popular this model is, this report is. Yeah, and then I'll be introduce how to quickly start with the deep learning repo. And this is a hands-on session. So in this demo, we will together run the inference of a normal deep learning model, which is called NeuroBot, neural-to-fault transformer, which leverage the latest EEG foundation model and also the novel multi-scale spectral learning representation module. So NeuroBot can, as you might already see in the title of this model, so NeuroBot can translate neural signals, which is EEG signal here, to the corresponding fMRI time series. And NeuroBot support any configuration of EEG electrodes at the input when training from scratch, and any subset of the originally used EEG electrodes when performing inference with the pre-trained model. And this will be our demo file. I think most of you like, does anyone has the access to the GitHub repo page already? Okay, cool. Okay, so as you can see in the README file, there are 2 options. So one is a Google Colab, which is super convenient to run. So you could just simply copy that link to your browser and save a copy under your Google account, and then you should be good to go. And if you want to run it on your local machine, you can just follow the README file there and download all the resources and set it up on your own computer. But if you haven't done this already, I recommend you now to use Colab with me because I have all the command line ready for you to install all this environment and data set instruction. Yeah, and if you want to download the code, here is where you can download the whole report. Okay, when you prepared all of this like environments, I could further introduce like how you can get quick started with this repo. So we already found it and it's so usable. So what's next? So the first thing to do is to get familiar with the repo. So first, understand the repo's structure. Here are some common files and folders usually appears in the deep learning repo. So um, definitely you want to read in detail about the reading file to get overview and how to use the model. And the next thing is to find the main script for the model training and inference, like the main script here and the train function or train loop here, and also the inference and predict. These code are basically where you start to run the whole repo. And I think the most important thing here is to, like before customizing anything, always test the repo with provided samples or sample data. So many repos would have this kind of sample data or pre-configured settings for you to have a quick start. However, some repo might not have, and you don't want to like download the whole data set because it can be super huge. What can I do for now? So the answer is we can send the random data in. So here are the examples for you to how to quickly send the random transfer into the model. So we first generate a random transfer that matches the input shape and required by model. Then we initialize the model and pass the generated tensor as the input here. And we can also print the output shape here just to get a sense of like what the output should look like. And the last thing, but I think is a very useful tips for you is to do this kind of testing. You could set the breakpoint either in like Visual Studio or Python just to run the code step by step to observe how the model processes these kind of features. Yeah, this is helpful. It's really helpful for you to kind of like get familiar with the model itself. And we also have this demo code in our demo as well. So you could, after you have run all of these blocks here, import the libraries, and then go to section point 2. Here is a very quick code for you to initialize the model. And since Neurable, it requires you to send the electron name here. So I have the prepared for you. And we have random data, and we simply send the model in. So the random data, the first dimension is the number of samples. So as you can see here, each return sample size, like the sample size of 8. So which just makes sense because our model only predict like one value at each time. Yeah, and then I will quickly introduce the general workflow for deep learning training. So first, you will get a data ready. Of course, you process your data, standardize it, and optionally augment it. And this is where you normally manipulate the data. And then you pick or build a model by yourself and to pick the loss function, and then build the whole training loop, and then fit the model, evaluate, and improve, and save and reload and complete this kind of loop again and again until your loss conversion. Yeah, and what if you don't want to train a model but only want to run the inference? Like now there are a bunch of like foundation models that was trained or trained on a large of data set like image, text, audio, brain signals, and this model, and you only want to pass the data through the model to get the latent embedding for some downstream tasks like classification, regression, or only just use it for inference. So it's even simpler. So there would be no training things here. You are not updating your gradient. You can only you can just load the like the pre-trained weights provided by the model and then send the data in, and basically that's it. And yeah, and then we will going to run the whole inference pipeline in our demo. Okay. Um, So first step, data preparation. We could first look at what our data set looks like. So our input will be EEG. EEG, it will be a multi-channel time series with this red marker indicating the collection, each collection of fMRI scan. And our output will be a RI time course extracted using the Fumo Atlas. And here we are predicting the thalamus. So here I also have the code for you to visualize all we have for our atlas. So we only pick the thalamus time course here as our input. And then we also have the function for you to pre-process your data. Yeah, and below here is where you call this function. And before call function, you need to have some like configurations of the settings. So here, the scan names and RNA names, we are putting thalamus here, and we are doing intra-scan prediction, which is which means the model was trained and tested on the same scan. And we run this, and it gives me the number of training, validation, and test. And then we use this block of code to prepare a model. So we initialize it, and we load the pre-train weight here, and it tells you all the key metrics successfully. Yeah, and then we are going to run inference. So as I said, Neurobot would require like input channel names at the input. So here I have the 4 channel names for you. For now, we are sending all the channels into the model. So we have 26 channels here, and we run this block to kind of get an index of each channel, and then we will send this index into the model. And the code here is doing the inference. So you can see we extract the data from the data loader, and then we send the data into the model. And it gives me output, which is what I have here. And we also have the script for visualize the results. So you can run this block, and then it should return a figure like this. So purple line is the predicted signal from thalamus, and the gray line is the ground truth. So you can see that our model can align with the ground truth quite well, reaching near like 0.8 correlation. And there's something else I think you can also play with this model. So as I mentioned, our Neurobot model can support any number of subset channels as our input. So here, you could choose any channels you want and put it into the channel name input variable. So here I'm picking 8 channels as example here, just to show how our model would perform under this subset of channels. Yeah, and we run this and run the block again. And it should give you 2 plots, like one is the new result and one is the original full channel version result. So you can see when we are using only 8 channels here, it still gives me quite like good results. So it drops only by like 0.02, which means our model is effectively learning some correlation information from all of this EEG channel data. And you can even only send 1 channel into the model. So in the next session, you could pick any channel you like. For example, here I pick C4, which is here, just to see if our model can still predict under 1 channel input. So we run this again, and yeah, and run the block again. And it returns just 3 plots, like compared with the previous one. So not surprisingly, like using only 1 channel here, the performance dropped a lot. And you can play with this module for like looping over all the channels to kind of see like which channel plays a very most important role to predict the thalamus signal. Yeah, and That's for the inference part. And for the fine tune and training, I think these are like exactly, I would say mostly the same compared with the this general workflow I mentioned. But one thing here is that if you are used a model that was trained for example, classification test, but now you are going to use that on the regression test, you might probably would like to consider to change a loss function here, which is suitable for your own test. For example, if you're changing classification to regression, you probably want to change the loss from cross entropy to mean square error. And besides, you can also train your model based on the previous pre-train weights. So basically, you could just load the your model before the load the model weights before training, and then you can just fine tune it, which is basically the same as fine tuning on your own data set. Yeah, and I think that's basically the things this workshop will cover. So a few takeaway tips for this. So first, documentation first. Always read the README file and installation guides. This is super important. And the second thing is start small. Which means you always run examples or demo script before training the full models. The third is seek help and check the issues on GitHub or contact the authors for clarification. And last thing is stay updated. You could subscribe to archive alerts or author social media for updates or related research or some new publications. Yeah, and last, I would like to thank all of our Nerdy Lab members and our Neural team. I thank them for their contribution to this project. And that will be all. And thank you so much. I would like to take any questions, and I will be around for these 2 days. So if you're interested in this model or have any questions, just feel free to reach out to me. Thank you. Oh, yeah, sure, go ahead. Thank you. Mhm. Yeah. Mhm. Yeah, so this is a very good question, and we answered this question like again. We have presenting our posters. So yeah, so I think fMRI is definitely a very powerful modality because it can do like whole brain mapping, it can do 4D, and it has a very high spatial resolution. So it's invaluable for academic research. However, one of the main drawbacks for fMRI is it's like super expensive and it's slow and it like suffers from like hemodynamic delay, so you can not really tell very precisely temporally about the neural activity. So yeah, and in general, like fMRI is much more or less accessible because expensive and medical like people with medical income cannot go into that machines. So we kind of like the very straightforward motivation is to we want to find a modality that was much more easier accessible to kind of like get this information from MRI. And the modality here we have for now is EEG. So EEG is very cheap and it's have a very high temporal resolution. And it can just tell you very precisely like which time what kind of like neural activity is happening, and it's directly it's electro signal. However, EEG has its drawback. So it can only measure the surface brain data. It cannot go into very deep. Another thing is EEG has a very low spatial resolution, so you cannot hardly you can just hardly tell that like where exactly in the brain is responsible for this kind of like activity. So these are all like motivation. We want to build this kind of like deep learning model to translate the EEG signal to fMRI. It can not only augment ability of EEG, because EEG originally cannot get the deep brain information, but now we can, for example, as shown in the demo here, we can now get the thalamus activity. And another thing is like EEG data, I think there are like much more EEG data available on the like publicly. So if we build this kind of like tool, so maybe we could just largely like augment our data set. Yeah, this basically like was our motivation to do this. And another thing is like by learning this kind of like projection from neural to bold, we believe there is something new happening here in that model, so which can be individual specific, which can be maybe can be a biomarker or something, but we don't know yet. But we just build this model and see, oh, it's promising. And I think our next step is to kind of learn this learn projections to test this in different populations to see if there's anything different between like for example, two different groups. Yeah. Mm. Yeah, I think, yeah, probably, yes. I think like hopefully we could get something unique, like we only can get from this projection, but not only like by EEG, either by EEG or fMRI, because yeah, so we think this kind of projection, it's like learning the hemodynamic response function might be very useful to like this kind of like research. Yeah. Yeah. Any other thing? Yeah. Yeah. Yeah, it's a good question. So when I designed this kind of window lens, I'm considering the length of hemodynamic response function, which is like about 20 seconds. And I think the most of peak and values most took place in the first maybe 16 or 15 seconds. And one practical things here is like, I mean, because in our model, we are also adapting a EEG foundation model in our model. So the pre-train weights of that model only support 16 seconds. So this is a very like straightforward reason why we use 16 seconds. But we think it's fine because like, as I mentioned, like a lot of peaks values are already covered in this like 16-second bills. Yeah. Mm. Any other questions? Yeah. Yeah, thanks. Yeah. Yeah, I think definitely, but now I haven't figured out like how to do this. But one of the possible approaches is to study in the latent space. But I think yeah, I don't have a very like clear path to like visit this, but I think one of the idea I already have is to kind of like, but it's different from this model, but to let a neural network to learn kind of like coefficient in hemodynamic response function, like the latency and how large is the peak, to let a network to learn this coefficient, then convolve this maybe the hemodynamic response function with the original EEG signal and see how well the model can predict. Yeah, that's possibly one idea, but yeah, we haven't tried it out yet. Yeah, yeah, that's true. Yes, yes. Mhm. Yeah, thank you. Any other questions? Okay, I think that's all. Thank you so much for your attention. Yeah.